Welcome, everyone. Today we are diving into a brand new explainer, and we're going to unravel the absolutely amazing journey that light takes through our atmosphere. You know, we look up and take the sky for granted every single day, but the truth is, light is actually running this invisible, chaotic obstacle course from the exact moment it hits Earth's atmosphere right up until it reaches our eyes.
And it all really boils down to one incredibly fascinating mystery. Think about it. If the light coming directly from the sun is white, which is basically just a mashup of all the colors of the rainbow, why does our sky constantly change colors, right? Why is it a calming blue at noon, a brilliant red in the evening, and then sometimes this terrifying orange during a wildfire? Okay, let's dive into this and find out exactly what's happening right above our heads.
So, Section 1, the everyday blue sky.
To really get a grip on atmospheric color, we first need to define the fundamental rule of the game, and that is a process called scattering. Scattering is quite simply the redirection of light in all directions when it hits gases or particles floating around in the atmosphere. See, light naturally just wants to travel in a straight line, but our atmosphere is packed with these microscopic roadblocks that basically force the light to bounce and bend.
Let's walk through exactly how this plays out step by step. In step 1, pure white sunlight hits the outer edges of Earth's atmosphere. Then, step 2, this is where the magic happens. Light travels in waves, and different colors have different wavelengths. Blue light travels in these short, choppy waves, while red light travels in long, lazy waves. Because the gas molecules in our air are so incredibly tiny, they specifically catch and scatter those short blue light waves in every direction. So moving to step 3, when you look up away from the sun, your eyes are literally collecting those scattered blue waves bouncing around the sky. And that is exactly why the sky looks blue overhead.
Moving on to Section 2, the physics of scattering.
Now, what's really interesting here is the sheer precision involved. Physicists don't just guess how light bounces. They actually use a particle's size, its shape, and the exact angle of the incoming light to calculate the probability of where that light will end up. It's a calculation known as a differential cross-section. It's a highly complex interaction, for sure, but scientists have neatly divided the whole thing into a couple of main theories.
The two dominant frameworks here are Rayleigh theory and Mie theory. On one hand, Rayleigh's theory deals with those extremely tiny gas molecules we just talked about, things like nitrogen and oxygen. They act like microscopic pinballs, specifically for short blue waves. This is the actual math behind our clear blue skies. But on the flip side, we have Mie theory. This applies to larger aerosol particles. We're talking things sized between 0.1 and 1 micrometer, like urban smog, dust, and soot. Because these particles are bulkier, they don't just scatter blue light. They interact with all wavelengths. This is precisely why highly polluted cities often have these hazy, white or gray skies instead of a crisp blue. The obstacles are simply too big.
Which brings us to Section 3, wildfires and hellish skies.
2.5 million. That is the number of acres that burned across the U.S. West Coast during severe recent wildfire seasons. The sheer scale of this destruction didn't just impact the ground. It pumped unbelievable, truly unprecedented amounts of smoke and debris straight into the atmosphere, which fundamentally altered how light reached the surface.
When this happens, the sky completely transforms into this deeply unsettling apocalyptic orange. Those dense smoke plumes hover high up, way up between 20,000 and 30,000 feet. And the smoke particles are so massive and densely packed that they act like a giant, heavy atmospheric filter. Those short blue wavelengths, they're completely blocked. They get scattered away before they even come close to the ground. The only light waves long and strong enough to push through that thick smog are the warm-toned ones, the reds and oranges. So the orange completely overwhelms the sky because it's literally the only light surviving the journey.
And honestly, it can get so extreme that even the red light fails. As UCLA climate scientist Daniel Swain points out, dense concentrations of these extreme particles can actually spawn fire thunderstorms. The smoke becomes so incredibly thick that it can block out the sun completely, plunging entire regions into total eerie darkness right in the middle of the day.
And hey, speaking of eerie skies, here's a fantastic twist of planetary physics for you. On Mars, the visual effect is the exact opposite of Earth's. Because the Martian atmosphere is super thin and constantly filled with fine red dust, its daytime sky actually looks red or orange. But when the sun sets on Mars, it turns this beautiful blue-gray color. It's the exact same physics of scattering, just interacting with a totally different set of atmospheric obstacles.
Let's shift our focus to the night sky now for Section 4, decoding lunar eclipses.
So, the crucial point here is this. During a lunar eclipse, the Earth doesn't just cast a giant, completely black shadow. As Earth moves perfectly between the sun and the moon, it does block direct light, sure. But some sunlight actually grazes the edges of our planet and bends right through our atmosphere. Just like a sunset, our atmosphere scatters away the blue light, which allows only the longer red and orange wavelengths to pass through and project onto the lunar surface. So essentially, a lunar eclipse is the visual result of every single sunrise and sunset happening on Earth at the exact same time, projected onto the moon. How cool is that?
And the color of that projection is incredibly informative. If we see a vibrant orange or red moon, it tells us that Earth's atmosphere is generally clear. But if the eclipse looks dim, brown, or kind of a deep copper color, it means our atmosphere is choked with obstacles. High levels of aerosols, wildfire smoke, or maybe recent volcanic ash are physically blocking even those long red waves from making it through to the moon.
This isn't just a pretty sight either. It's hard data. NASA scientists actually use these eclipse colors to gauge what they call aerosol optical depth. By comparing the visual color of the moon during an eclipse to satellite maps, researchers can measure exactly how much light atmospheric particles are blocking. It turns out the moon acts like a giant natural mirror reflecting the overall health and clarity of Earth's air.
Finally, let's explore Section 5, the elusive green flash.
I am talking about the famous green flash. This is a phenomenon that occurs right at the very last moment of sunset or the very first instant of sunrise. Just as the sun dips below a clear, unobstructed horizon, like if you're looking out over the ocean, a distinct green spot or rim briefly flares right above the sun's upper edge. It is incredibly fast, usually lasting no more than 2 seconds. And it's caused by the atmosphere refracting or bending the different wavelengths of light at slightly different angles as they pass through the thickest part of our atmosphere.
Now, a totally natural question you might have here is, well, if the shortest wavelengths bend the most, why isn't it a blue flash? And the answer ties directly back to what we learned earlier about the blue sky. While blue light definitely is refracted the most, it is also preferentially scattered right out of your line of sight by the time it travels through that much dense air at the horizon. So the blue gets scattered away entirely, leaving green as the final surviving visible color to hit your eyes before the sun vanishes.
And this brilliantly illustrates that the green flash isn't just one single thing. It actually comes in several distinct variations, depending on the atmospheric mirage conditions. For example, the inferior mirage flash looks like a flattened oval, and that happens when the ocean's surface is warmer than the air. The Mach mirage creates this pinched-off fin strip when there's an inversion layer. The subduct flash makes the top of the sun look like a green hourglass. And then there's the ultra-rare green ray, which actually shoots a literal beam of green light straight up into hazy air.
While these flashes usually just last a second or two, extreme mirage conditions can totally bend the rules. Back in 1934, members of the Richard Evelyn Byrd Exploration Party in Antarctica witnessed an absolutely incredible event. Thanks to the unique freezing barrier surface of the ice creating a massive mirage effect, the green rim was essentially frozen in time. They watched it appear and disappear for 35 minutes straight, just by moving their heads up and down a few inches.
This rare optical trick is so captivating that it's left a massive mark on our culture too. Jules Verne's 1882 novel, aptly titled The Green Ray, really helped popularize the phenomenon, framing it not just as a trick of scattering light, but as this magical, romantic moment of ultimate clarity. It's popped up everywhere since, from Disney's Pirates of the Caribbean to Pokémon, always signifying something mystical. But as we now know, the real magic is just the brilliant physics of our atmosphere.
We've seen how tiny gas molecules paint our sky blue, how thick smoke forces it to glow orange, and how lunar eclipses and green flashes reveal the invisible particles floating around in the air. Every single color above us is a direct reflection of what's happening right here on Earth. So the next time you look up, I want you to ask yourself, what are the colors telling you about the air you're breathing today? Thank you so much for joining me on this explainer. Keep your eyes on the sky, and I'll catch you next time.